So hi everybody, welcome to the last colloquium actually in this year. So we will actually make a break after this one for the holidays, and we will start again next or in spring. I'm actually very happy about our colloquium speaker that we have today. So Professor Daniele Faccio. Daniele is a Royal Academy Chair of Emerging Technologies at the University of Glasgow. And he obtained his PhD in physics in 2007. And since then, he had like many very prestigious faculty and visiting faculty positions. And he joined the University of Glasgow in 2017. And actually to emphasize one of his prestigious positions in particular, he also is adjunct professor at the Wine College of.
That's the most prestigious one,
yeah. So yes, of course, Daniele has won like a lot of prizes and awards, but he told me specifically that I should not talk about it. And he said, like, if somebody's interested in this, you should look up his CV. So please look up his CV if you're interested in these awards.
Thank you.
And I should also say that Daniele is trying to visit the college basically every year, and he's around like always like in late fall. So if you want to talk to him, if you have an idea for potential collaborations, he's like a very open person. So please feel free to approach him, and I can guarantee you it will be fun. Okay, so now let's come to the talk. The talk topic today is quantum mechanics in rotation. I'm happy that I made a note for that because it's actually not on this slide. Yes, and I think we are all very excited about the talk. And Daniele, the stage is yours.
Thank you, Florian. Thank you for a very kind introduction. So yeah, great to be here. So I have been visiting at least once a year for quite a while now, and hopefully we'll continue to do so. So it'd be great to connect up with anyone who wants to chat. I've got lots of friends here that I've made over the years. So it's really an honor and a pleasure to be here today. So I wanted to just give a very quick, just got 2 slides, not so much about myself, but about what the research group does, because today I'll be talking about just one research topic in the group, but we actually do quite a bit more. So we, over the past year, we've moved into this brand new building at the University of Glasgow, the Advanced Research Centre. And what's great about this building, which I think is going to be in some sense similar to the building that you guys are getting just next door, is that there's a lot going on. It's not just physics and engineering. We've got one level devoted to photonics and quantum science. But then on the next floor, we've got the bioengineers, the biologists, the pharmacologists, and then another floor up, we've got chemistry. And sort of interspersed through this, we've also got social sciences and arts, and it's really unique environment, and have to say has really changed the way in which we do research over in Glasgow. So I'm hoping the building you'll be getting will give you sort of the same kind of opportunities. So I lead this what we call the extreme light group. It's called that historical reason, so I won't go into the details of that. But at the moment, we count about 35 researchers, and we divide the team into three labs. There's the quantum photonics or the quantum lab. That's some of the research that we do in that lab is what I'll be talking about today. So entanglement and curved space. I won't waste any more words on that just now. Then we have the human augmentation lab, where we're working on various things, but mainly focused around the human, the brain, and how you can use that to interact in different ways with the world, and specifically with AI. We're doing things like edge computing with the brain and neuromorphics, but also developing wearable and contactless sensors for human augmentation. And then the third lab is the computational imaging lab. This is, for example, in the context of doing some work with Ewan Wright and with Florian, where we're working on a range of things, but all focused on computational imaging. So sensor fusion for example, microscopy, but also things like non-line of sight imaging. Okay. So onto the main topic of today's discussion then. So I'm going to talk to you about quantum mechanics in rotation. I'll start out straight away by saying most of this talk actually is not going to be about quantum mechanics at all, but will mostly be about rotation. So, but why look at this idea of sort of quantum mechanics in rotation anyway? So we have quantum mechanics and general relativity, I would argue, are two of the most successful theories in physics that we have at the moment, or have ever had. But there is no theory of quantum gravity. And essentially, the short version of this, what it boils down to is that we don't understand gravity, and we don't really understand quantum mechanics either. I mean, the maths works. That's not understanding. Okay, so the maths is fine. That's why these theories work extraordinarily well, which in a sense makes things even more worrying. No one has been able to falsify these theories at the mathematical level, and yet we don't understand what is going on. So that's the problem statement. We do, however, have some semi-classical theories. That's typically where you would start when faced with the problem of developing a quantum theory. And in the context of GR, I'm referring, for example, to several effects, but everything started off, the development of these semi-classical theories, I'd say, really kicked off with work by Roger Penrose. He published in 1969 a paper on gravitational collapse. It's a very long paper, and there's 2 pages in there where he talks about this concept of superradiance. We'll come to that in the next slide. Very interesting concept. Now, that's connected then to another topic that we'll be talking about quite a lot about, by this effect called Zel'dovich amplification, which was introduced a couple of years later, mainly to try and understand what Penrose was talking about. And these sort of ideas then eventually fed into what is known as Hawking radiation and the concept of black hole evaporation. Again, a semi-classical theory of how quantum vacuum behaves in the surroundings of a black hole described by general relativity. So let's start from Penrose's idea. So this is for those who know Penrose, he makes these beautiful hand drawings. And in the paper that I'm quoting here, he shows this picture, and he's talking about how an alien civilization might potentially be able to extract energy from a black hole. And so an obvious mechanism is to have, so it built like a structure surrounding your black hole, and then you're just lowering on a you're lowering a spring-loaded mass into the black hole, and then when this mass reaches the event horizon, you let it go, and the recoil of the spring will give you back mc squared energy. But then he's pointing out that there's another approach to do this, where you can gain even more energy if the black hole is also rotating. You can extract the rotational energy from the black hole by, and this is the weird thing, so the black hole is rotating this direction, and you take the scaffolding where you're sitting on, and it has to co-rotate with the black hole, albeit a bit slower. Now you do the same thing. You lower your spring-loaded mass, you let it go, and as it traverses what is called the ergosphere, you will get back an energy. You'll get back your mc squared, of course, but you'll get an additional term, which is due to extraction of energy from the rotational energy of the black hole. And when he's talking about all of this, he is there's no maths, and there's basically just a paragraph, and there's a lot of reference to negative energies and negative frequencies, and it all kind of makes sense when you read it, but there's no maths. There's nothing really supporting why this would actually happen. So let me skip this. So this is where Zel'dovich comes in. He was thinking about this problem, at least according to the account by Kip Thorne in his book, and trying to figure out if there's a different system, different way of understanding what is going on here. So what Zel'dovich did, he replaced the notion of a rotating black hole with that of a rotating absorbing cylinder. Okay, so you can look at a black hole, you've got an event horizon that basically is your perfect absorber. Anything that hits it gets sucked in and never comes out again. Replace that with a metallic cylinder, and now you can use Maxwell's equations or the equations of electromagnetism and maybe try to put some maths against this problem. Okay, And what he noticed was that he wasn't talking about orbital angular momentum back then, because that's a terminology that appeared much later on. But the words are describing effectively this concept of sending in an electromagnetic wave that has orbital angular momentum, so it has a phase winding, and you send that onto a cylinder which is also rotating. And what he noticed was that the absorption of the cylinder when you go into the reference frame of the cylinder, there's a rotational Doppler shift. So this wave will shift in frequency. And so you have the absorption is multiplied by this rotational Doppler shift term, where this is the electromagnetic wave frequency, this is the rotation frequency of the cylinder, and this is the OEM winding number. So if you just put m equals to 1, for example, so the phase rotates from 0 to 2 pi in one wind, then basically you're just asking that the cylinder rotates a little bit faster than the oscillation frequency of the electromagnetic wave. And then the Doppler shift will shift this to negative values, and negative absorption is just gain, okay? And so that would explain how you can then have a mechanism whereby, I mean, this energy, so it means that this wave will then reflect off the cylinder, but it will have a higher amplitude due to that reflection. And of course, the energy for that is coming from the rotational energy of the cylinder, which will be slowed down by this energy extraction. Okay. So, and that then, as I mentioned earlier on, led these sort of ideas, because I forgot to mention Zel'dovich in that paper and also in subsequent papers was then also pointing out that you don't actually necessarily have to send in a wave yourself. The quantum vacuum already has these waves in it. And so potentially this mechanism could be, again, he wasn't using the words quantum friction. We can call it quantum friction, but essentially would be able to excite fluctuations, energy out of the quantum vacuum through this mechanism. So all these ideas sort of gradually led into Hawking's proposal in 1974 that black holes could evaporate and eventually explode. And various people, including Bill Unruh, we'll come back to him in the next slide as well, played a big role in sort of the development of these semi-classical theories, and published, for example, a paper on how to mine energy from a black hole, and went through the details of actually how much energy you could extract. The answer is it's a lot. So I started off quite a few years ago working on a related concept introduced actually by the same Bill Unruh, who published in 1981 a paper where he noted the analogy, the formal analogy in the maths between a flow in a hydrodynamical scenario, so flowing water, for example, and the maths of curved space-time. And he's pointing out that that analogy could actually lead even to the formation of the analog of a horizon in a flowing fluid, and that could then be used to study Hawking radiation, albeit, yeah.
Where the Schrödinger equation has a nonlinear term. I forgot the name of the equation now, but it has a that depends on the amplitude of the wave function.
Okay.
Then there are analogy also between fluid mechanics and quantum mechanics here. Is there like any work that tried to combine the three?
Not that I'm aware of.
Mechanics?
That's interesting. No, not that I'm aware of. Mm-hmm. So, and so this proposal from Bill Unruh led to sort of there's a whole field of analog gravity where people are trying to use this concept of hydrodynamics. And hydrodynamics in a broad sense, you can use, I approach this using light. You can generate effectively fluids using light. And so you can build upon these analogies between formal analogies in the maths between various systems, and you can pull out curved space-times from the geometries that you can create in these analog systems and try to study things like Hawking radiation. But the point is, though, one needs to be careful. I put real these are not real in sort of inverted commas experiments, because you're never actually dealing with gravity. It becomes then maybe more of a debate for philosophers as to whether these experiments actually reveal anything about what happens around a black hole, because that's never what you're probing. You're never probing gravity, and actually most of the time you're never even probing quantum mechanics. It's classical fields propagating in a classical fluid, so there's no GR and there's no quantum. However, the maths do map. So if the maths maps, then one would think that the physics does as well, other than you don't know. I would argue, as someone who's worked in this field for 10 years, you don't know what you don't know. So what we have been, so we've shifted our attention over the past several years in the group from this field of analog gravity more towards, again, real inverted commas experiments that actually probe the original problem, quantum gravity. These are far and few between. There are very few experiments that really try to try to probe quantum and gravity. They are much harder, but I think also they're a lot more exciting. And so the rest of this talk would be sort of trying to explain how we go from these concepts that I've introduced to where we are today, where I think we're actually trying to probe the generation of entanglement in curved space.
A vortex, and then there's sending away something similar to this. Amplification happens to the scatter wave.
Yes.
From the vortex.
Yes.
Is that an analog gravity type?
That is an analog gravity experiment. Yes. It's so that is that's a work by Silke Weinfurtner and her team, and Bill Unruh is one of the co-authors, and indeed that I would argue that was the first demonstration of Penrose superradiance from a rotating space-time geometry. Yeah. So what I really like about the proposal from Zel'dovich, where you have this rotating cylinder and then you try to send waves onto it and you look at the reflection, is that this is no longer, okay, one might argue it's not a curved space-time anymore, but it could be quantum, but also it's the real deal. I mean, this is not an analog anymore. If you can take, I mean, he was talking about a real condensed matter system. There's a real cylinder, send in some waves and you try to measure this superradiance. I don't need to emulate it or try to map the maths of that problem onto something else. It's electromagnetism. This is something we can actually try to deal with. The problem, though, is the actual technical feasibility of the Zel'dovich proposal, because you'll recall what you have to do is rotate your cylinder faster than the frequency of your electromagnetic wave. I mean, if you're in the optical regime, we're talking petahertz, and that's just impossible. And so what I'm showing here in this graph, I'm trying to trace out the, so there's some assumptions being made here, which then I will go ahead and break, because that will be the solution to the problem. But it's a first approximation. If you want to do what Zel'dovich was saying, so you want to have a wave that's interacting with an object, with a cylinder, you'll probably want, ideally, you'll want that object to have a size which is larger than the wavelength of the wave that you're sending on. Otherwise, you're in the sub-wavelength regime, and the efficiency, usually, the efficiency of the interaction will go to zero. So you need a cylinder which has a length which is at least or larger than this quantity here. This is the rotation frequency. So basically, I want the length to be larger than the wavelength of my electromagnetic radiation. So that puts me up here in terms of, so on this axis, I'm just plotting the rotation frequency, and then over here I'm plotting, okay, what would the cylinder length need to be if it has to be larger than the wavelength, and to satisfy the Zel'dovich condition, you have to sit up here. And then you go and look at what's available in literature and technology in terms of how fast can actually, what are the fastest things that have been rotated in nature. And you've got this sort of technology feasibility region, which sits all the way down here. So there's some papers there. You've got everything from just simple dentist drill all the way to levitated nanoparticles. Okay, so there's no overlap there.
Toward when you shine a laser beam at it, and it gets reflected, it gets Doppler shifted, blue shifted.
Yeah.
So you extract energy from the moving mirror. In what way is this different?
You extract energy, so you extract energy because you change the frequency of the photon. You don't change the photon number. This does not change the frequency. So there's a Doppler shift when I move into the reference frame here, but the scattered wave then anti-Doppler shifts back. So the frequency of the incoming and outgoing wave are the same. The photon number is not. You haven't conserved photon number. That is what I define by amplification. If you're talking about between the incoming and outgoing wave, no, they have the same frequency, but they have different photon number. Okay. Yeah. Okay. So that's sort of the problem statement, and it's an issue. I mean, that's simply, there's no technology that allows you to go here if you stick to this idea that the size of your cylinder has to be greater than the wavelength of the wave that you want to amplify. And there are many papers, including some of my own, out there pointing out this difficulty and looking for trying to do these experiments in different regimes. So looking, for example, at acoustics. So this is where we went to. And I started a collaboration here with Miles Paget, as a colleague at the University of Glasgow. He's well known for a number of things, but in particular for his work with orbital angular momentum. He's one of the pioneers working in this field, mainly with optics, but also with acoustics. At the time, he had only just published this very nifty paper where he had basically built a ring of speakers, so it's all talking sound now, with some tubes that basically bring the sound in onto a disc, which is spinning, and he had some microphones on this disc so that he could listen to the sound being received, but the sound is now being listened to in the rotating frame. And the reason he was doing this experiment because he was interested in the rotational Doppler shift. And this is what he saw. So he plotted this graph in this paper where basically, so what you're looking at here is the rotation rate of this disk. Okay, and this is the actual measured frequency by these microphones. And you can see the Doppler shift. Let's just take, so L equals 0, nothing happens. There is no, the omega minus, so this is what we had, was M in our formula. Omega minus L, omega is, if L equals 0, there's no Doppler shift. But if we take this one, L equals 4, okay, so it means you have 0 to 8 pi. Doppler shifts all the way down. The energy kind of seems to disappear here. That's because you're starting to hit DC, okay? And then you keep on rotating fast and it comes back again. But you've shifted, you've gone, I mean, what's happened is you keep on going, the frequency has become negative. You've Doppler shifted all the way through DC to negative frequencies. The way this manifests itself is, lots of debates with Miro last year around what a negative frequency actually means. You can't actually directly measure a negative frequency. The way this manifests itself is what you measure here is a flip in the sign of the OEM. You have the perception that the OEM has changed from -4 to +4. But this is what caught my attention for two reasons. First of all, he managed to find a way, this is the first time I think anybody had seen this, he managed to find a way to rotationally Doppler shift a frequency all the way through DC to negative frequencies in a rotating system. And these are exactly the ingredients that one needs to try and look at the Zel'dovich effect. So we got together, and so this is just another photo of the setup. Marion was a PhD student at the time working on this. And we tried to observe not only the negative frequency Doppler shift, but also try and see if we could have an amplification associated to that. So here we're looking now at the actual amplitude of the sound. We have two cases. We have one where the absorber, so that we had a piece of foam, which is absorbing sound, and we could either attach that to the rotating wheel or detach it. So when you detach it, the microphones are still rotating, but the absorber is not. And so what you're seeing here, the amplitude is going all the way down to 0 when you hit DC, and then it comes back up again, but you have the same energy as you had that you sent in. But now if you attach the absorber, and that is also rotating the microphones, now you see that when you reach up here, well, even actually as you pass through DC, you can already see straight away here, you already have, this is where the Zel'dovich condition happens, omega minus capital omega is less than 0, you have amplification. And actually the amplification is significant, it's quite high. So I've got a little video, it's not connected to the audio, but hopefully you'll be able to just hear it from the speakers. You can actually, because it's sound, you can actually play this sound back as you move, as you increase the speed of the spinning disc. Okay, so that what you heard there, I'm not sure if it was running again. Okay, it's not that obvious to hear, but the amplitude is also higher when you get to the opposite end, to the end of the recording. So you're listening, this recording, exactly, this recording is in the rotating reference frame, so there is a Doppler shift there. Right, so no, because the amplitude has changed. Yeah, so but it's because, well, I don't know whether we should be talking about phonons here, but it's the actual amplitude of the sound that's changed. So you can verify this by just rotating the absorber and detaching the microphones, and you'll still see the sound amplitude go up. The point of putting the microphones in rotation is because if you go in the rotating frame, because of the Doppler shift that I see, I can separate out the various OEM orders coming from the speakers, so I can isolate L equals 1, 2, 3, 4, and so on. Whereas if I'm because I use the different Doppler shifts to do that. Whereas if I put myself in the lab frame where there is no Doppler shift, the sound, everything's superimposed, the frequency is all one and the same for everything, and it's a lot harder to separate out those various terms. Does that make sense? Yes. There's that, and also across this condition, I think I'm not sure if I've got a plot on this for electromagnetic. We've got some. I can give you some papers where we've done all the calculations in the electromagnetic theory case, which we'll get to in a moment. I'm not sure I'm showing very many equations in this talk, so I can't remember if I've got those. But you have across the Zel'dovich condition, on one side you had the curve sort of does this. So you've got across that condition, just to the right, you have maximum gain, and then it comes back down a bit. But just to the left, you have an additional absorption. So it's a bit more, you have a bit more absorption than just due to the absorber itself. Well, it should slow down. So if it's really spinning, you're extracting the rotational energy out of that, yes. Whether it's a good way of doing that, we need to discuss. Yeah. Mm-hmm.
If I understand correctly, this is locally measuring amplitude, right? So what if the red curve is just looking at some kind of a local interference maximum? It doesn't tell you about the energy measured in the whole system. So is it not amplification?
It's rotating though, so you'd have to find some weird situation where that maximum, that interference maximum is somehow also co-rotating with your disk, regardless of the speed at which you rotate it. That sounds very unlikely. right? So remember, so what I'm doing here is I've got disk rotation frequency. So this disk is rotating, and I'm accelerating the speed at which it's rotating. So in order for what you're saying to be true, I'd have to have some kind of maximum of interference, which is also rotating. But then when I decide to change the disk rotation frequency, it also has to rotate a bit faster. I mean, why would it do that? It would.
And making a conclusion about something local. So, and the red microphone is sitting on the. Where is it? Is it in the lab or is it over there?
No, so these in both cases, the microphone is sitting on rotating disk in this case. Okay. So the take-home messages from this acoustical. So this is not the electromagnetic wave thing that Zel'dovich wanted yet, but there are some take-home messages from this. So the Doppler shifting can lead to measurable negative frequency effects. The wave, what we also realize is that the wave matter coupling can be extremely strong. In Zel'dovich's original paper, he's already complaining about the fact that if you use OEM beams have a zero intensity because there's a phase singularity, so intensity goes to zero. So if I want to put a cylinder in the center, but there's no light because I'm using OEM, and so there's no way, at least in his proposal, there was no way out of this. You're left with this exponentially weak interaction between the electromagnetic wave and your cylinder. But what we have here is a totally different geometry. We're working in the near field. We have these tubes forcing, and the wavelength of these sound waves is 30 plus, between 30 and 100 meters. And yet the interaction zone is this big. We're bringing these waves in. We're working in the evanescent field or near field region, and going, rather than trying to hit the cylinder from the outside, we're actually forcing the waves to go through it. And this is the trick. So you're no longer constrained by the fact that your medium, your cylinder, has to be of order wavelength or larger. It can be a lot thinner and a lot smaller as long as you find a way to constrain those waves to interact with the cylinder in this near field region. And so that is exactly what we then, we understood that, we went back to the problem of electromagnetic waves. And I think I've just got one slide on this today. I won't go into the full details, but this is what we built. So we effectively built a toroid with a solenoid that can induce an oscillating magnetic field inside the toroid. And then we have a rotating metallic cylinder here. And the idea is that we will rotate this at a frequency which is larger than the oscillation frequency of the magnetic fields that we're inducing the toroid. And the frequencies that we're working at here are hundreds of hertz. So the wavelength here is huge. Okay, it's hundreds of meters, kilometers even, depending on the frequency that you choose. But we're in the super near field regime, and we're confining the field and the interaction to happen here. So I'm not going to go through any of the maths, but you can model this as an effective circuit. Basically, what we do is we measure the voltage and we measure the return phase of the radiation of the field that we send in. And from that, using this circuit analog, you can pull out a model that doesn't have any free parameters once you've measured V and the voltage and its phase. But you can use that formula to pull out the effective resistance of this cylinder. And you can see that as we sweep the wave frequency across the Zel'dovich condition, which is the dashed line here, we go from a positive resistance to negative. So negative resistance means, again, this would be positive. So positive resistance means you've got absorption. The negative resistance means that you have, you're going to have amplification. So this is, I think, the first demonstration of actual Zel'dovich amplification using electromagnetic waves. So quite excited by this. The referees seem less excited, but we'll get there. The direction we're going now is to try and cool everything. So this is still classical waves. There's nothing quantum. To go quantum, we need to cool this to very low temperatures. And that's where things get tricky, because ideally you want to cool this down to the ground state. And that can mean extremely low temperatures. And this is we're building a theory around that right now, with the idea of starting to cool things down and see if we can actually observe the first proposal we've got that we want to try out will still be in sort of this thermal regime where you've got a thermal background, but there will be a quantum contribution, which we think we should be able to distill out of the data. Well spotted, yes. So in doing all of this, we discovered, and we now explicitly talk about this in the paper, there is a really very tight connection between this and how you generate electricity from a wind farm. So those are, there's a slight difference in that those induction generators don't use a solid core. They use what is called something like a squirrel cage. So it's a circuit. The rotor is made of an RLC circuit, which is rotating inside an external RLC circuit. But the physics, we believe, is exactly the same. If you look at the maths, and we're talking maths from the 1940s here, they talk about a slip frequency. And when you look at what the slip frequency is, it's omega minus capital omega. It's exactly the same formula. And they point out that you get amplification when the slip frequency becomes negative. They're using different words. It's not a solid cylinder, so it's not the absorption that's flipping sign. It's the inductance or the resistance that's flipping sign. But what I didn't know and realized only after is that not all of these generators work in the same way, but I think about 80% of them work using this principle, meaning that in order to work, they have to be connected to the grid. So you have to send in an electromagnetic wave, your 50 hertz. You have to send that in, and then that wave essentially gets reflected and amplified in the process. And if it's not connected to the grid, you don't get anything out. It's not the standard sort of induction mechanism. It really is using this effect. So I'm happy to talk about that further later on, but it's really interesting that this Zel'dovich effect, actually, I mean, the engineers had sort of latched this. Of course, they didn't make this connection. They didn't realize this is what they were doing. But yes, there's a very tight connection with induction generators. Well spotted. So spoken about this. So back to the problem of quantum gravity. So there are many theories. I mean, this is just copied out of Wikipedia. It's a Wikipedia entry. And there are many theories of quantum gravity: string theory, loop quantum gravity, M theory, and it just goes on. And the problem why there's so many is because, I would argue, because we don't have any experiments to guide us in deciding what's right and what's wrong. We just don't have any data. But on the other hand, then, okay, so if you search Wikipedia for quantum gravity experiments, there's not much there. And the problem is, there's a reason for this, is because most or all of those theories that I listed predict effects at the Planck scale. So meaning that if you want to do an experiment that verifies or falsifies or collects data for these theories, you need to be probing at 10 to the minus 43 seconds or 10 to the minus 3 meters, depending on how you want to look at it. But we just don't have that capability at the moment, and probably won't have it for a very long time. So a few years ago, slightly different idea emerged, which we latched onto because I think it's extremely interesting. So rather than trying to solve what one might call the hard problem of quantum gravity, probing at the Planck scale, is there an easier problem of quantum gravity? And so there are two papers published back to back in 2017 in PRL, where the authors were proposing a mechanism by which you can try and probe. So you're not trying to collect any more data about how gravity or quantum mechanics merge together, but you're asking the question, is gravity quantum? Can I find evidence of the quantum nature of gravity? It's a slightly different question. Turns out it's a lot easier to answer, and it is within technological reach. Hasn't been answered yet experimentally, but I think the community is getting there, and we will get there, I think, within the next several years. So their proposal is quite simple. It's what I call the Marletto-Boser hypothesis from first authors of the two papers. You take two particles which are not entangled, so totally separated and separable. You put them in two superposition state, for example, it could be in a which path superposition state, okay? And then these two guys will have an interaction which is stronger than these two guys, or in the limits, these two external guys won't interact at all. These two will. The important bit is that this interaction has to be mediated only and nothing else than by the gravitational field between these two massive particles, okay? And under those conditions, what they demonstrated, actually this extends beyond gravity, it's in general. If you want to understand if your interaction is of a quantum nature, then you can apply this same concept. And under these conditions, you can demonstrate that if you then bring these back together again and you measure you can measure entanglement between these two particles at the output of your experiment, and you see there's entanglement, then that is proof that that interaction was of a quantum nature. Okay. Well, that's why things are hard. That's why the experiments, it's taking a while to do the experiments, because you need to make sure that you can isolate out or factor out all other interactions and keep only gravitational interaction. That's the hard bit. But it's a much simpler problem, I would argue, than trying to probe physics at the Planck scale. I don't know the details of the spin experiment, but I can talk to the details of photon-based experiments. I'll show in the next slide. But yes, you need to do something that removes everything except the gravitational interaction.
How far which path need to be?
No, I mean, the further up, the larger the difference, then the easier it is to, or the shorter the interaction time probably will need to be in order to then actually observe the entanglement. I mean, if these are so close that they're basically the same thing, then everything's interacting and you won't see generation of entanglement at the output. So the more you space them apart, the better. I know that's a bit hand waving, but then one needs to dig down into the details.
But also the coherence.
Yes. So the trade-offs. Okay. So what we asked ourselves, I mean, in that proposal, there's no talk of photons, but can we test the quantumness of gravity with photons? I think that's extremely unlikely, using this approach at least, because of the very weak interaction of gravity with photons. But you can try to do something similar and ask the question, can we test the quantumness or the quantum nature of space-time with photons? And the point here is that photons, for example, are very sensitive to rotation. This is a photograph of a Michelson interferometer, a Sagnac interferometer that Michelson built in 1925, where he was able to measure rotation. I mean, we know, I mean, this is obvious now, but that was the first time that somebody measured the rotation of the Earth using light. So light can have very high sensitivity to rotational motion. So this is where I'm going to start to talk. I'm running out of time, so I'll accelerate a little bit. Okay. So this is where we then start to talk a little bit about quantum optics, and we bring in, my group has been working for a long time on the concept of Hongel-Mandel interference or photon bunching. And this is a very efficient sort of sensing technique, and it relies on quantum interference. So it's a very simple idea. You take your two photons, you overlap them on a beam splitter, and there's no maths here, but you can write out the basically four possible options for where these two incoming photons can emerge from the other side of the beam splitter. But these two will cancel out if your two photons are completely indistinguishable in all degrees of freedom. And so then what you'll see is you change the delay in one of the two arms here, you'll see that when the two photons are, the delay is so large that you move beyond the coherence time of the individual photons, you'll just have sort of the classical 50-50 splitting of photons at the output. But when you are at delay, and I'm looking at the coincidence rate, by the way, I'm looking at, you know, how many times do I see a photon at each output port from the beam splitter? You see this probability goes to 0, meaning that the photons are bunching. Every time the two photons arrive at the same time in the beam splitter, they are forced to both exit the same output port. You don't know which one, but they will both exit the same output port. Okay, so then we took this sensing technique, this Hongo-Mandel so it's called Hongo-Mandel after the 3 researchers who first introduced the technique, and we put this on a rotating table. And so it's the schematic is relatively simple, but then getting this right was a bit harder. But basically what you're seeing there is just the measurement of the Hongo-Mandel dip. So we're scanning a delay, and then we put the table in rotation, and basically what we see is that the dip just simply shifts. So you're shifting the time at which the photon bunching occurs. So here's a video of the actual experiment. So yeah, this was because there's let me get rid of that. There's a belt which was vibrating. So so basically what we have is you've got the photon counting electronics underneath. You've got the lasers and the crystals and the setup above. What you're seeing here is basically 100 meters of optical fiber, which is sort of round around a circle, so 1 meter diameter, to sort of give sufficient path length to accumulate the delays that we see in the experiments. So this is rotating only at about 1 hertz. That's already sufficient to see these effects. So the next experiment we did, so that was just, in a sense, this was trivial, because basically you're using the fact that you have this sort of Sagnac delay, which is changing the arrival time between the two photons at the final beam splitter. So it wasn't totally unexpected that this dip would shift in delay, and would shift by exactly the same amount that you would measure with a classical Sagnac measurement. So what we then tried to do is move more towards the question, okay, how does entanglement interact with something like this? And what we're using here is a very sort of interesting point that Anton Zeilinger noticed, is that if you can have situations where instead of a dip, you have a peak in your Hongo-Mandel interference. So basically what is happening, what that means is that your bosons are now behaving like fermions. Rather than bunching, they are always anti-bunching. They always exit opposite ports. And the way to do this is, and this is what Anton was pointing out in this paper, is so in general, you can write any quantum state as a sum of those 4 Bell states. When I have a dip here, the state that I have here can be written, it could in principle be any sort of combination or sum of these 3 symmetric Bell states, symmetric, so we continue acting as bosons. But this state here can only be generated by this single antisymmetric Bell state. But what that means is, when I see this, I can know for certain that this is the only pure Bell state that I've excited, meaning that any photons that did this had to be entangled. There's no other option, okay, because that's what a pure Bell state is. Whereas in this case, it could in principle be a mixture of these, so I can't really say anything about the entanglement. So that's why he was saying antisymmetrization reveals hidden entanglement, okay, because in the dip it's hidden. I don't know if the photons are entangled, but if I see this, I know that they were entangled. So combine this with work by Xi and his colleagues, where he now took the you have to love the drawings, by the way. There are no mirrors or anything here, but he took the standard sort of, this is your Hongo-Mandel beam splitter, but now he put in an additional interferometer here. You have a short arm and a long arm. This is a Psychomax-Zender. And what he noticed was that as you change the distance between the long path and the short path, you can indeed flip the Hongo-Mandel dip into a peak.
So that you get a peak. By assuming the phase shift. But then it will be all the free states will get a peak.
Yes, so you can't change it though, it's fixed.
Yeah, you won't know the entanglement out of it, but it's.
But the point here is that this is tunable. As I shift by lambda, it will go back and forth. So you'll see this dip oscillate up and down. Okay, so that's the trick we're going to use. So so we had this. This is the sort of schematical overview of the setup, where now we have a nested interferometer. Again, now that this nested interferometer is in the form of a Sagnac interferometer, so it's sensitive to rotation. So, and again, so I want to point out that as you change the length of this, or the length difference in that cavity, this dip flips up and down. It goes from a dip, so you can't say anything, that the entanglement has disappeared. It becomes a peak, the entanglement has appeared, and it disappears, appears, disappears as you change the delay. Okay, so this is what we did. So the nested interferometer now is a Sagnac interferometer. So as you increase the speed, you'll be increasing the phase shift you get. And what we see indeed is, again, so we're scanning the delay here in the Hongomandel interferometer. And so this is the main Hongomandel dip that you'd expect if there was no nested interferometer. And then you have these side peaks over here, which are just the classical peaks that you expect. So you can have interference with the short path and interference with the long path. But then you've got these two additional peaks, which is what I call the quantum peaks, which I'm not going to try and explain right now, because every time I get lost. They are really odd. They shouldn't be there. These appear at delays that sit in between the long path and the short path. There is no physical path in the system that actually corresponds to photons arriving with this arrival time, and yet you see an interference peak. Just trust me on that. That's how it is. But these are the peaks, though. These quantum peaks are the ones that when you start rotating, they flip. So these peaks are due to a quantum interference effect. And these are the ones that when you start rotating, you start inducing a relative phase shift between the rotating and counter-rotating photons. You pick up the phase shift, which flips the dip into a peak. So what we have here is a manifestation of how non-inertial motion can take a photon pair where entanglement was not visible, and it can then render it manifest just by simple rotation. So this again is a different visualization of the same data now. Just simply as we increase the rotation speed, you can see the dip disappear and then become a peak. Okay, so the very last result that I wanted to show you. So summarizing, we've shown that we can. For the first experiment, we showed that when we put a Hongomandel interferometer in rotation, we can shift the position or the time at which quantum interference happens. Then we did a second experiment where we showed that we can hide or extract entanglement from the photon pair. But the real question we wanted to ask, this is all a build-up to asking this question: can we generate entanglement, actually generate the entanglement? So there was none before, now I'm going to generate it with the rotation alone. So that alone is important, coming back to the point of you need to isolate it from anything else. But with photons, that's easy because photons don't interact with other photons. So they'll only interact with the rotation. And again, coming back to the Marletta-Bose hypothesis, what you need to do is you need to take your photons, put them in which path superposition, let them interact with the rotation, bring them back together again, and then see if you've generated entanglement. So it's basically just a modification of the previous experiment, where now we have single photons coming in and we split them on a beam splitter. Because it's a single photon, you put it in the superposition state of going either left or right, which then means either going into this interferometer, which has a small radius, or into this interferometer, which has a large radius. And in doing that, you effectively generate a superposition between two rotating spacetimes. Okay, I no longer know whether my single photon is rotating in the small Sagnac interferometer or in the large Sagnac interferometer. And because they have different radii, that effectively means that they're experiencing two different accelerations as they rotate. Okay, so that's the maths. I won't go into the detail of it, but this is the point I was trying to make, that you can either look at this as a superposition of the rotations or the superposition of the paths. And when you go through the maths, there's basically what you find is you can measure something called, for example, the concurrence, which is this curve here. And you can see as you start rotating, you have no entanglement, but then if you get the rotation rates correct, and it's still very low, it's still just 1 Hertz, you can observe perfect entanglement. Now, this scheme only uses 1 photon. And so there's an ongoing debate. I mean, it's nothing to do with us. It's an ongoing debate as to whether entanglement with a single photon actually qualifies as bona fide quantum entanglement, in the sense that you should also be probing for non-locality. How do you do that if you only have 1 particle? Because most measurements, for example, if you want to do a Bell inequality measurement, requires having 2 particles, where I measure something on 1 particle, something on the other, and I look at the non-local correlations between those measurements. If I only have 1 photon, you can't with 1 photon, as far as I know, do a Bell inequality measurement. People have tried to come up with schemes where you can transfer the entanglement from a single photon onto 2 photons, but I haven't seen any experiments where these theoretical proposals have actually been put in place. So I don't have any slides on this, but we have, so we published that result, received the criticism, accepted it, understood. We now have a scheme where it's very similar, it's basically the same setup, but now we have 2 single photon sources that enter the system that are totally independent. They come from 2 different lasers, and you can generate polarization entanglement at the output. So hopefully we'll be preparing that and submitting that soon. But the point is that these rotation frequencies are low, meaning that in principle, we could even go back to the Michelson experiment and just build a large enough interferometer, which actually doesn't have to be that large. We're talking several hundred by several hundred meters. And we could, the prediction is that we would observe the generation of entanglement from independent input particles or photons due to the rotation of the Earth. Of course, that wouldn't add anything to the physics of doing it on a tabletop experiment, but I still think it's pretty cool. So this is my last slide. I think these are really exciting times for an experimentalist. Experiments, I think, now can be done in the lab, trying to look at the problem of quantum gravity. I think hints on the horizon for larger scale, Earth scale sort of measurements that will link quantum gravity. There are a number of other experiments underway that I didn't mention, but there's recent work by Philip Walter from Vienna using noon states in a Sagnac interferometer to increase the sensitivity. Ron Follman at Ben Gurion is working on the exact same concept proposed by Boson and Marletto. You've got Hendrik Albrecht at Southampton working with optomechanics and so on. I don't have time to list all of them, but there's quite a lot going on in the field, and I think there's going to be some big breakthroughs over the next several years. Thank you.
Yeah, thank you, Daniele, for this fascinating talk. I personally learned a lot today. So we have open questions. Amit.
Gravity, but was the experiment with the Q-dip you showed on one of these slides?
Which
we have these 2 Q-dips, quantum dips in the Sagnac interferometer.
Let's go back. Where was it? No, it's
for yes, there goes 2 Q. So is that? I mean, I'm just speculating. Is that the non-locality, which is
no?
Basically,
it's So the easiest way to look at this is to sit down and draw out the Feynman diagrams, which is what they also do in the papers. I think it's interesting that it's only these papers that seem to resort to actually drawing out the Feynman diagrams to try and explain what is going on, because I think it's hinting the fact. I'm not sure how many people really understand where that interference, how that interference works, but it is about so for example, so a hint of what is going on is the temporal resolution of your detector has to be larger than the time difference that you're using here. So if I have sufficient time difference, I can actually see the difference between the long and short. These peaks disappear. But another way of saying what is going on is that the interference, so do I have the interferometer here? Yeah, this guy. So a single photon, so one photon goes here and does its thing. Another photon, this bit here is a single photon interferometer. Depending on, so one photon comes in, and then I need to look at the photon that comes out. By changing the relative phase between, or the phase in this interferometer, changing the interference, you are effectively antisymmetrizing the biphoton state at the output. Just by changing how the interference here occurs of that single photon. Yes. So that is basically what it says. That's what you're controlling there.
That doesn't
Yes.
explain why this still exists. That's symmetrization.
Yes, exactly.
I was curious about the plot where you showed that Q-dip alternating in amplitude. It seems the initial amplitude, when you have 0 rotations, the initial amplitude, is that 0 or?
It's random in the sense that it depends. It's going to depend on the initial length difference between the two interferometer arms. So yeah, it doesn't. There's no physics or in there other than the two interferometers are slightly delayed. So remember what I was saying. If you're out of delay, you don't see a dip. So if you haven't matched, over 100 meters of fiber, it's really hard to have 200 meters worth of fiber that's exactly the same length. So you start off at the point where there is no interference, and you start rotating, then you see the interference appear, and then but remember, this is sensitive to changes. It's the nested interference, this is not the Hongo-Mandel interferometer I'm talking about. This is the nested interferometer, which is sensitive to phase changes. So all you need is for that interferometer to be offset by lambda over 2, and you won't see that quantum dip. That makes sense? Okay.
Walk me through the last part, because it seems very interesting. You're trying to draw an analogy with variables.
Yes.
And in that case, you have you're generating entanglement through gravity and
Through rotation.
no, in their case.
Oh, in their case.
Yeah. So, and then the contradiction between GR and quantum mechanics here is clear, because you cannot write GR as superposition of two different fields.
Mm-hmm.
So, and in your case, you're using the fact that rotation of a non-inertial reference frame,
Mm-hmm.
where now you have two spacetimes.
Yes.
And then you're generating entanglement through what? It seems that there's
generating a superposition. The experiment is generating a superposition in the space times instead of in the gravitational fields, and then that leads to entanglement.
Right. So this is where the confusion comes in, and that this is not sufficient to get entanglement. It's just a superposition.
No. So the photons coming out are actually, so the space times. So okay, let's go back to the Boser-Marletto sort of approach. You don't know anything about, you can't conclude that there are any gravitational fields that are entangled. That's not where the entanglement is. The entanglement is in the spin states of the particles that emerge at the output of the experiment. Same thing here. I can't tell you anything about entanglement between the space-times. That's not what I do. I generate a superposition between the space-times, but the entanglement is measured in the polarization states of the output photons.
Well, what
Yes.
outcomes would be?
I mean, if we believe the 2017 PRL papers, yes.
Yes.
I think you were next.
Okay. Hi, this is not a quantum question. You had this beautiful plot, like much earlier in the talk about the rotational Doppler shift of like acoustic stuff, with like that line that you saw like cross into the negative frequencies. Could you go back to that? Thanks. Yeah, that one. So I don't think this is a trick of the lighting, but I noticed that there's like harmonics in that plot that only seem to appear after this switch to the negative frequencies. Like they're really dim, right?
So you're looking at this guy, for example.
Yeah, and there's one below too. Like, is that like a microphone artifact, or is that like actually happening?
So I think this is actually happening. We went and redid the experiments, of course, but it might have been, so the intensity here is reflecting the amplitude. So it could have been that already in this experiment, they were already seeing this Zel'dovich effect. They didn't have the same absorber we had, but it's a thick piece of plastic. Plastic absorbs. So this guy actually, this one does have something coming in here with similar. It's barely visible. This guy though, I don't think it does. So this actually could have been. But I mean, even if you look at this guy, you can see it's more intense than this one. Kind of. The color scheme doesn't help, but I think they already were seeing this amplification already in those first experiments. Yeah, well spotted.
And we must question. In the end, you will have to prove and convince everybody that you can screen everything out. Right? Now you have a photon propagating the waveguide. How are you going to argue that this acceleration is not changing the waveguide? How are you going to screen out the interaction of the photon propagating in the waveguide? It's obviously interacting with the manner of the waveguide. So,
but it's the photon interaction with the other photon that counts. So how would that? I hear what you're saying, but you'd need to find what interaction are we talking about? I mean, one has to be realistic, right? I know that we can't know, but we know a lot. I mean, we know about how photons don't interact with other photons. We know how photons are guided through waveguides. We know what is going on. We can do measurements where the thing isn't rotating, and you've got that as a reference point, and then you put it in rotation. You can accelerate, so you can have various rotation rates and look at how the entanglement scales. You'd have to come up, I think, with something probably a lot more bizarre than quantum gravity to explain how the entanglement is emerging. And doesn't fit with your theory, by the way. So if I've got a theory and it fits with the theory, why would you think it's something that there's some unknown interaction that's going on there that's not known to humankind? I mean, that sounds like that would be a very weird statement to make. What I'm saying is, I do the experiment. Let's flip this around. I've got a theory. It predicts something, predicts a curve. I do an experiment. It predicts the curve. I say, oh, amazing! I found that. The rotation can induce entanglement. By the way, there's also very intuitive understanding, reasoning that one can go through to understand what is going on in terms of generating this entanglement between the polarizations. They say, no, maybe it's due to some unknown physical interaction between photons at distance that's got nothing to do with quantum mechanics. That would be a very odd thing to do.
The burden will be on you to show that it's.
But there are no other mechanisms. What mechanisms are there? I mean, that's the beauty of photons. I mean, photons don't interact.
It's a very weak interaction.
No, that's the Heinkel-Mandel effect. The Heinkel-Mandel effect, two photons come together and they interact. That's how you get two.
When they come together, exactly. That's the point. The only point in which they interact is at the beam splitters. But you can check for that interaction. You know exactly what photons do at a beam splitter. You can model that. You can measure it. You don't stop the thing rotating, and you can measure exactly what is going on. That's all under control. So that is not what is happening here, because otherwise, I mean, that would be trivial. You just create an interferometer and you see some. I'm saying they're not interacting. They're not interacting when they're in the. So whilst they're in the fiber, because that is where the magic is happening. It's where these phase shifts that accumulate and generate entanglement, that's where that's happening. So, or according to our theory, that's where it's happening. So you put that in rotation, that photon is nowhere near the other photon. I mean, what is left? Then they interact on the beam split at the output. Yes.
The waveguide. So I think there's a potential hole in the logic of the experiment. That you really are.
And you're really proposing something incredibly bizarre.
Well, I think I think that's a natural question.
Is it though? Let's discuss over coffee.
Okay, yeah. I just wanted to say so.
Probably.
We usually have long hikes. I mean, I should make sure clarify. This is being recorded. We don't hate each other. We usually fight about this, 10-hour long hikes, and it just goes on and on. So don't worry. And there's never a solution, exactly, because of course I'm always right, and he just doesn't want to admit this.
So Kevin, this has now to be a very good question.
A lot of pressure. Well, thank you. So I guess trying to understand, showing that the rotational Doppler shift negative frequencies occurs at the benchtop scenario, but wouldn't it be as much evidence to say if he has another black hole colliding with another one and then the outcoming after the collision, the change in orbital angular momentum, the black hole itself, and the exiting radiation, the justification?
Look, I think there's also a Nature Physics paper where the authors were proposing looking at radio waves scattered. I don't know what their origin would be, but coming from got a black hole, there's some source of radio waves, and those are scattered off the black hole, and you could pick up the angular momentum of the black hole, and you could measure that. I mean, there are scenarios out there where what you're saying could be possible. The problem at the moment, and we've got gravitational wave observatories now, so maybe in the future, and there are even theories, really exciting theories, where predicting that there could be some evidence of quantum gravity occurring, and that could be seen in deviations of those ripples from what you expect from just standard classical GR. The issue is, so yes, but it's not easy because we have the resolution that we have with the gravitational wave observatories at the moment, and those collisions, as you can imagine, are incredibly messy. It's not something very clean that happens. And it happens once, so it's not like I can do the measurements 100 times. It happens once, and then there would be another event, but it would be completely different because it would be neutron stars, or the masses would be different, or the collision rates would be different, and so on. But potentially, I see no reason why what you're saying one day won't happen. Someone will look at that and say, "Oh." Sorry?
Is there a limit to the level of amplification?
Well, I need to go back to the en route papers. I think there's a bit of discussion, but I think it's, if I remember correctly, it's 20%. I'm recording here, so I'm paper to be checked, but I think it's 20% of the total mass of the black hole. So it's huge. The numbers are sort of, people have gone through numbers. It would be enough to power civilization for the age of the universe, if you could go and extract that energy.
Okay. Great.
Yeah.
So,